This tutorial is all about two food additives. First of all, emulsifiers and then baking powder. These two products can both be put onto salad. One of them on the left, salad cream, which is this even white colour, and this second one on the right, which is salad dressing, which has got two layers, an oily layer on the top and a liquidy water layer on the bottom. Now both of these products actually contain oil and water, so why is it that the one on the left is all mixed up and doesn't need shaking, whereas the one on the right has two layers? And the answer is that one of them on the left has an emulsifier added. At foundation level, you need to know about emulsifier molecules and what they look like, whereas at a higher level you need to know how they stop the oil and the water from separating. Many different foods, particularly processed foods, contain emulsifiers. This mayonnaise, for example, contains the emulsifiers which are found naturally in egg yolk. It also contains mustard, which contains an emulsifying agent. Emulsifier molecules have two distinct parts to their molecule. On this diagram here, we can see there is a hydrophilic end, literally meaning loving water, and this end is able to make attractions and bonds with water molecules. The other end, which is a long hydrocarbon chain end, has a hydrophobic property, and this means that it does not like water and in fact makes attractions and bonds with oil or fat molecules instead. You might be expected to draw a molecule such as that and to label it in that way. The actual emulsifier molecules look like this diagram at the bottom. They have these water-loving or hydrophilic heads which can attract to water, and then they have these long water-hating tails or hydrophobic tails which attract to oil. At higher level, we might be expected to explain how this emulsifier molecule allows oil and water to mix and not to separate. You might be expected to draw a molecule, such as this one, and then draw water or oil molecules, or both, around the molecule to show which ones are attracted to which end. Emulsifiers are these special chemicals that allow not only the water and oil to mix, but also not to separate out. You end up with a mixture which is called an emulsion, and an emulsion is a mixture of oil and water that will not separate out. Two examples of emulsions are mayonnaise and salad cream, but there are many others such as these in the table. Butter, for example, has its main component as fat and has tiny droplets of water mixed in with it which don't separate out. Milk is the other way round. This one is mainly water with tiny droplets of fat which don't separate out. This GCSE question says, egg yolk is an emulsifier in mayonnaise. Egg yolk stops the water and oil from separating. Look at the diagram. It shows a molecule of an emulsifier. Explain how emulsifier molecules stop oil and water from separating. Use a labelled diagram to help you. We might start by drawing such a molecule as they've given us in the same sort of way, and then showing some water molecules attracted towards the hydrophilic end. We then may show some oil molecules, which I'll show as zigzag chains attracted towards the hydrophobic tail. Then might say or label that these are water molecules, that these are oil molecules, and then perhaps a sentence to say that the hydrophilic end attracts to water molecules, and the hydrophobic end attracts to oil molecules, this stops the oil and water from separating by making an emulsion. As you can see from the mark scheme, there's one mark for talking about the water being attracted to the hydrophilic end and one for the oil being attracted to the hydrophobic end, or you can get both marks by suitable diagram. Moving on now to a second food ingredient. Why do these two rise? The first one, the bread, rises because of the action of a microorganism, yeast, which contains enzymes that act on the flour and produce bubbles of carbon dioxide. But the cake rises by a different agent. This uses a chemical called baking powder, which is either added to the ingredients or added within one of the ingredients, self-raising flour. You need to know for foundation level the word equation for this decomposition of sodium hydrogen carbonate or baking powder, but at higher level be able to construct a balanced symbol equation for the same reaction. If you heat baking powder, which is sodium hydrogen carbonate, and pass any gas which is made through lime water, we see that the lime water turns cloudy. This tells us that carbon dioxide has been made. The word equation for this reaction is as given there, and you need to learn that equation, that sodium hydrogen carbonate makes sodium carbonate, also a white powder, plus water and carbon dioxide. For higher level, we need to also know the symbol equation, and you need to have learned the formulas of each of these substances. Sodium hydrogen carbonate is NaHCO3. Sodium carbonate is Na2CO3. Water is H2O, and carbon dioxide CO2. Now at present this does not balance, and the reason it doesn't balance is that the number of sodiums on each side is different. On the left there's 1, on the right there's 2. So we need to put a 2 in front of the sodium here. Let's just now check that everything else balances. We've got 2 sodiums and 2 sodiums on the right. We've now got 2 hydrogens on the left and also got 2 on the right. We've got 2 carbons on the left. Yes, we've got 2 carbons on the right, 1 in each of these 2 compounds, and then we've got 2 lots of 3, which is 6 oxygens, and we've got 3 here and another 4th and 5th and 6th one here, so that equation now balances. And finally, a past paper question on the topic we just looked at. Here it says sodium hydrogen carbonate, NaHCO3, is used in baking. When heated, it decomposes to sodium carbonate, Na2CO3, water and carbon dioxide. Write a balanced symbol equation for this reaction. Well, in this case, they actually give you the formula of sodium hydrogen carbonate and one of the products, Na2CO3, sodium carbonate. So we're going to score 1 point by getting the correct chemicals on the correct side of the equation. So on the left we'll have NaHCO3, and on the right we're going to have Na2CO3 and H2O and CO2. And then in order to balance the equation, as before, we see that there's 1 sodium on the left and 1 on the right. So we're going to put a 2 in front of there, which then, of course, satisfies the fact that we've got 2 hydrogens here and 2 here, and a total of 6 oxygens, 1, 2, 3, 4, 5, 6, and 2 carbons, 1 here and 1 here.